Hello there, and welcome to the Sleepy Library. Tonight, we are drifting into the magnificent realm of solar systems, where worlds stranger than you can imagine exist in a cosmic dance of time and gravity. Our own solar system is only one story in a vast library of celestial arrangements. Each star surrounded by its own family of planets, moons, rings, and mysteries. Out there in the silent dark are systems of twin suns, molten planets, and worlds floating free in the endless cosmos. This is not just a journey through space. It is a journey through wonder, into the hidden architecture of the universe. The things we will discover are not only strange, but beautifully real. These faraway systems might challenge what we think life needs, or what a planet even is. But for now, just breathe. Let the night sink around you and allow your mind to settle. Let's begin. Our solar system began as a vast, swirling cloud of gas and dust about 4.6 billion years ago. Imagine it, a gigantic nebula floating through the darkness of space, made up of hydrogen, helium, and tiny grains of stardust left behind by earlier generations of stars that had lived and died. This cloud was enormous, stretching across light years, turning slowly in the void. Something disturbed it, perhaps the shockwave from a nearby supernova, a dying star's last violent breath rippling through space. That gentle push was enough. The cloud began to collapse under its own gravity, pulling inward, spinning faster as it fell. Over hundreds of thousands of years, most of the material gathered at the center, growing hotter and denser, until nuclear fusion ignited and our sun was born. But not all the material went into the star. About 0.1% remained, orbiting in a flat disk around the newborn sun, a protoplanetary disk where the planets would form. This disk was not uniform. Near the sun, temperatures soared hot enough to vaporize ice and keep only the hardiest materials solid. Metals and rocky minerals could condense there, tiny grains that stuck together when they collided. Farther out, beyond what astronomers call the frost line, temperatures dropped low enough for water ice, ammonia, and methane to freeze solid. This difference in temperature created a cosmic recipe that determined what kind of planets would form where. Close to the sun, where only rock and metal survived, the terrestrial planets took shape: Mercury, Venus, Earth, and Mars. Beyond the frost line, ice joined rock to create much larger building blocks. These grew massive enough to capture the abundant hydrogen and helium gas still swirling in the disk, becoming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. The process was slow and patient. Dust grains drifted through the disk, bumping into each other, sometimes sticking together through static electricity and molecular forces. Pebble by pebble, boulder by boulder, these clumps grew. When they reached about 1 kilometer across, gravity became strong enough to pull in more material and growth accelerated. These were planetesimals, the building blocks of worlds. They collided and merged, or shattered and tried again. Over millions of years, the largest ones swept up everything in their orbital paths, clearing lanes through the disk. The smaller debris either joined the growing planets, was flung into distant orbits, or fell into the sun. What began as a shapeless cloud became an ordered system, planets spaced in relatively stable orbits, all moving in the same direction around their star. But our solar system did not form in isolation. The entire process unfolded within a stellar nursery, a region of space where thousands of stars were being born at once. These stellar nurseries are found throughout the galaxy, enormous clouds of gas and dust called molecular clouds. They are some of the most beautiful structures in space, glowing with the light of newborn stars, their edges sculpted by stellar winds into towering pillars and sweeping curves. Our Sun formed in such a place, surrounded by sibling stars, all born from the same parent cloud. Over time, the gravitational interactions between these young stars scattered them across the galaxy. Today, the Sun's siblings are lost among countless other stars, their shared origin hidden by billions of years of motion. But somewhere out there, stars with the same age and chemical composition as our Sun still shine, distant cousins in the great family of the Milky Way. The story of how planets form is not unique to our Sun. Across the galaxy, around nearly every star, similar dramas unfold. Astronomers have observed protoplanetary disks around young stars in stellar nurseries like the Orion Nebula, catching planet formation in the act. In 2014, the Atacama Large Millimeter Array Telescope captured an extraordinary image of a young star called HL Tauri, surrounded by a disk with distinct gaps and rings. These gaps are likely being carved by forming planets, sweeping material out of their orbits even as they grow. The image looks almost exactly like artistic renderings of how our own solar system must have appeared 4.6 billion years ago. It confirmed that the basic picture, the nebula hypothesis first proposed centuries ago, was correct. Solar systems form from collapsing clouds, and planets grow within the disks that surround newborn stars. But not all solar systems form the same way. Some grow around not one star, but two. Binary star systems are common in the galaxy, with roughly half of all stars having at least one stellar companion. For many years, astronomers wondered whether planets could form in such systems. The gravitational pull from two stars, each tugging on the disk in different ways, could disrupt the delicate process of planet formation, scattering planetesimals before they could grow large enough to become planets. Yet observations have proven that planets can and do form around binary stars. Some orbit just one of the two stars, threading a careful path through the gravitational landscape. Others orbit both stars at once, in what are called circumbinary orbits, following paths that loop around the entire binary pair. The first circumbinary planet around main sequence stars was discovered in 2011 by NASA's Kepler Space Telescope. The planet, called Kepler-16b, orbits two stars locked in a tight dance, circling each other every 41 days. The planet itself takes 229 days to complete one orbit around the pair. From its surface, if it had one you could stand on, you would see two suns rising and setting, one slightly larger and brighter than the other, casting double shadows across the landscape. The discovery of Kepler-16b opened the door to a new understanding of planetary systems. Binary stars, once thought too chaotic for planet formation, could host entire families of worlds. Since then, dozens more circumbinary planets have been found. Some orbit red dwarf binary pairs, where both stars are small and cool. Others circle sun-like stars, or even stranger combinations. In 2025, astronomers announced the discovery of TOI 2267, a binary system with not one, but three Earth-sized planets. Two of the planets orbit one star, while the third orbits the other, making it the first known system where both stars in a binary host transiting planets. The stars themselves are separated by 8 astronomical units, roughly the distance between our Sun and Saturn, close enough that their gravitational influence on each other is significant. Yet the planets remain stable, locked in orbits that have likely persisted for billions of years. This discovery challenges the notion that close binary systems are hostile to planetary formation. Instead, it suggests that Earth-sized worlds may be common, even in complex gravitational environments. Planets in binary systems can follow surprising paths. Some orbit one star in what's called an S-type orbit, staying close enough that the second star appears as a bright but distant companion in the sky. Others follow P-type or circumbinary orbits, looping around both stars. The stability of these orbits depends on the separation between the stars and the planet's distance from them. If a planet orbits too close to a widely separated binary pair, the competing gravitational pulls will eventually tear its orbit apart. But if the binary is tight and the planet orbits far enough away, or if the planet stays close to one star while the other is distant, stable configurations can persist for billions of years. The existence of planets in binary systems has profound implications. About half the stars in the Milky Way are in multiple star systems, which means that roughly half of all potential planetary systems could be orbiting binary or even triple stars. For decades, this vast swath of the galaxy was thought to be largely barren of planets, too chaotic for stable worlds to form. Now we know better. Planets can form in binary systems, sometimes in the habitable zone, where liquid water might exist on their surfaces. One such planet, discovered in a binary system 3,000 light-years from Earth, orbits one of the stars at almost the same distance Earth orbits the Sun. Though the planet is cold because its host star is much dimmer than our Sun, the discovery showed that Earth-like orbits are possible even around binary stars. If a similar planet orbited a Sun-like star in a binary system, it could have conditions suitable for life. This greatly expands the number of places in the galaxy where habitable worlds might exist. Not all planets stay where they form. Planetary migration, the process by which planets move from their birthplace to new orbits, is now understood to be a common and dramatic part of solar system evolution. When planets form within a gas-rich protoplanetary disk, they interact gravitationally with the disk material. These interactions create waves and perturbations in the disk, transferring angular momentum between the planet and the gas. Depending on the specifics, a planet can either spiral inward toward the star or drift outward. In many cases, planets migrate inward, sometimes traveling vast distances over millions of years. The most striking evidence for planetary migration comes from a class of exoplanets called hot Jupiters. These are gas giant planets, similar in mass to Jupiter, but orbiting incredibly close to their stars, often completing an orbit in just a few days. The discovery of the first hot Jupiter, 51 Pegasi b, in 1995 was a shock. According to the standard model of planet formation, gas giants should form beyond the frost line, where ices can condense to build large cores. Close to a star, temperatures are far too high for ice to exist, and there simply isn't enough solid material in such a small region to build a massive core capable of capturing gas. The only plausible explanation was that 51 Pegasi b formed much farther out and then migrated inward. Several mechanisms can drive this migration. During the gas disk phase, gravitational interactions with spiral density waves in the disk can cause planets to lose angular momentum and spiral toward the star, a process called Type II migration. After the gas disk dissipates, planets can still migrate through gravitational interactions with each other, or with leftover planetesimals. In some cases, a planet is flung onto a highly elliptical orbit by a close encounter with another massive planet. These eccentric orbits can bring the planet very close to the star at closest approach. Tidal forces between the planet and the star then act as a brake, sapping energy from the orbit and causing it to gradually shrink and circularize. Over hundreds of millions or billions of years, the planet settles into a tight circular orbit, becoming a hot Jupiter. Astronomers have found planets caught in the act of this migration. In 2024, a team announced the discovery of TIC 2412495330b, a gas giant with one of the most extreme orbits ever observed. The planet's orbit has an eccentricity of 0.94, meaning it follows a highly stretched ellipse. At its closest approach, it passes 10 times closer to its star than Mercury is to our Sun, experiencing temperatures that can vaporize rock. At its farthest point, it swings out to a distance comparable to Earth's orbit. The planet also orbits in a retrograde direction, moving opposite to the star's rotation, a sign of a violent past involving gravitational encounters with other bodies. Simulations show that tidal forces will gradually shrink and circularize this orbit. In about 1 billion years, the planet will settle into a close, circular path, becoming a full-fledged hot Jupiter. This planet is a snapshot of migration in progress, offering a rare glimpse into a process that usually unfolds over timescales far longer than human observation. Migration can reshape entire solar systems. In our own solar system, it's thought that Jupiter and Saturn underwent a period of migration early in the solar system's history. This migration, described by the Nice model, may have scattered Uranus and Neptune outward, destabilized the asteroid belt, and triggered a bombardment of the inner planets by comets and asteroids. The evidence for this comes from the current orbital configuration of the giant planets, which suggests they did not form where they are now, and from the timing of the late heavy bombardment, a period roughly 4 billion years ago when the Moon and inner planets were heavily cratered by impacts. Migration is not just a curiosity of distant exoplanet systems. It likely played a crucial role in shaping the solar system we call home. While most planets orbit stars, some wander through space alone. These are rogue planets, also called free-floating planets or isolated planetary mass objects. They have no parent star, no sun to warm them, no light to guide them. They drift through the darkness between stars, cold and silent, warmed only by the faint heat left over from their formation and the slow decay of radioactive elements in their cores. Rogue planets are difficult to detect because they emit almost no light. Their surfaces are frozen, their atmospheres collapsed into ice or thin hazes. They glow faintly in infrared wavelengths, radiating the last whispers of internal heat. But this glow is so feeble that only the most sensitive telescopes can detect it, and only if the planet passes relatively close to us. Most rogue planets are found through a technique called gravitational microlensing. When a massive object, like a rogue planet, passes between a distant star and Earth, its gravity bends the starlight, acting like a lens. For a brief time, usually hours to days, the background star appears to brighten. By studying the pattern of this brightening, astronomers can determine the mass of the object that caused it. Microlensing surveys have detected signals consistent with rogue planets, some as massive as Jupiter, others as small as Earth. The data suggests that rogue planets are astonishingly common. One study estimated that there could be nearly 2 Jupiter-mass rogue planets for every star in the Milky Way. Another suggested that Earth-mass rogue planets might be even more abundant, with trillions wandering the galaxy. If these estimates are correct, rogue planets may outnumber stars by a factor of 20 or more, making them one of the most numerous types of objects in the galaxy. How do planets become rogues? There are two main pathways. Some rogue planets may form in the same way stars do, from the direct collapse of gas clouds, but without gathering enough mass to ignite nuclear fusion. These objects blur the line between planets and brown dwarfs, the so-called failed stars. Others are ejected from the planetary systems where they originally formed. During the chaotic early days of a solar system, when planets are still jostling for position, gravitational encounters can fling a planet onto a trajectory that escapes the star's gravity. Once freed, the planet drifts through interstellar space, potentially for billions of years. Some may eventually be captured by another star, becoming part of a new system. Others will wander forever, solitary nomads in the vast dark. The idea of a rogue planet is both haunting and fascinating. On such a world, there would be no day or night as we know it, no cycle of sunrise and sunset, only eternal darkness punctuated by the faint light of distant stars. Without a sun, the surface would be frozen, temperatures plunging to just a few dozen degrees above absolute zero. Any atmosphere would condense and freeze, forming layers of ice kilometers thick. Yet beneath this frozen crust, conditions might be more hospitable. Radioactive decay in the planet's core could generate heat, potentially maintaining a subsurface ocean of liquid water. If the planet had a large moon, tidal forces could provide additional warmth. In these hidden oceans, far from any sun, life might conceivably exist, thriving in the dark on geothermal energy and chemical nutrients. Rogue planets are more than just curiosities. They offer a unique opportunity to study planetary atmospheres and interiors without the blinding light of a nearby star. They also highlight the diversity of outcomes in planetary formation. Not every planet finds a stable, long-lasting home. Some are cast out, doomed to wander. But even in exile, they carry the story of their origin, the chemical fingerprints of the star and disk from which they formed. By studying rogue planets, astronomers learn about the frequency of planetary ejection, the dynamics of early solar systems, and the range of environments where planets can exist. Solar systems are not static. They evolve over billions of years, shaped by migration, collisions, and the slow burn of stellar aging. Some systems are orderly, with planets moving in nearly circular orbits, all in the same plane, like a well-choreographed dance. Others are chaotic, with planets on tilted, elongated paths, the scars of violent encounters still visible in their motion. The architecture of a solar system tells a story, a record of its history written in the orbits of its worlds. Consider the system of Kepler-16, the first circumbinary planet discovered. The two stars orbit each other in just over 41 days, locked in a tight gravitational embrace. The planet orbits both stars at a distance where it receives about the same amount of light as Venus gets from the Sun. But because the stars are cooler than the Sun, the planet is colder. Still, its orbit is stable, safely beyond the chaotic region too close to the binary pair. The planet is a gas giant, unlikely to have a solid surface, but moons could orbit it, and those moons might be rocky, warmed by tidal forces, perhaps even habitable. The Kepler-16 system is a reminder that solar systems come in endless varieties, and what seems impossible by the standards of our own system can be perfectly normal elsewhere. Another extraordinary system is TOI 2267, discovered recently by citizen scientists analyzing data from NASA's TESS satellite. This system contains two red dwarf stars orbiting each other every few hundred days, separated by 8 astronomical units. Around these stars, 3 Earth-sized planets have been detected, all in tight orbits, completing their years in just a few days. Computer simulations show that the system can only remain stable if the 3 planets do not all orbit the same star. Instead, 2 must orbit one star, while the third orbits the other. This arrangement is breathtakingly delicate, a balance of gravitational forces that has somehow persisted for what must be millions or billions of years. The planets are too close to their stars to be habitable, their surfaces likely scorched by intense stellar radiation. But the fact that they exist at all, in such a crowded and complex gravitational environment, is a testament to the resilience of planetary systems. Planets can form in systems far stranger than our own. Some stars are part of triple or even quadruple systems, where 3 or 4 stars orbit a common center of mass in intricate patterns. Finding planets in such systems might seem implausible, but they have been detected. These planets must navigate a gravitational landscape far more complex than anything in our solar system, threading paths through multiple stellar gravitational wells, yet somehow finding stable orbits. Their existence expands the boundaries of where we think planets can survive, and suggests that even in the most chaotic stellar environments, planets can find a way. The diversity of solar systems challenges our assumptions. For decades, astronomers used our own solar system as the template for understanding planetary formation. It seemed logical. Rocky planets close in, gas giants farther out, everything orbiting in the same direction in nearly the same plane. But the discovery of exoplanets shattered this comfortable picture. Hot Jupiters orbit closer to their stars than Mercury is to the Sun. Super-Earths, planets larger than Earth but smaller than Neptune, are incredibly common around other stars, but absent from our own system. Some planets orbit in highly tilted or even retrograde orbits. Others have densities that defy explanation, too puffy or too dense for simple models. The galaxy is filled with solar systems that look nothing like ours, each one a unique experiment in planetary formation and evolution. One of the most intriguing classes of exoplanets is the super-Earth. These planets have masses between Earth and Neptune, roughly 2 to 10 times Earth's mass, and they are the most common type of exoplanet found so far. Our solar system does not have a super-Earth, which makes them all the more interesting. What are they made of? Some might be rocky, with thick atmospheres of hydrogen and helium. Others could be ocean worlds, covered entirely by deep seas of liquid water. Still others might be mini Neptunes, with small rocky cores surrounded by thick envelopes of gas. Because we don't have one to study up close, super-Earths remain mysterious. But their ubiquity suggests that they are a natural outcome of planet formation under conditions slightly different from those in our solar system. The habitable zone, the region around a star where liquid water can exist on a planet's surface, is different for every star. Around a hot, luminous star, the habitable zone is farther out. Around a cool, dim red dwarf, it is much closer. Some planets orbit right in the middle of their star's habitable zone, receiving just the right amount of warmth. But being in the habitable zone does not guarantee habitability. A planet also needs the right atmosphere, the right mass to hold onto that atmosphere, and a stable climate. Venus is technically in the Sun's habitable zone, but its thick carbon dioxide atmosphere has created a runaway greenhouse effect, making the surface hot enough to melt lead. Mars is also on the edge of the habitable zone, but it lost most of its atmosphere long ago, leaving it cold and dry. Habitability is not just about distance from a star, it is about a delicate balance of many factors. Around red dwarf stars, the most common type of star in the galaxy, habitable zones are close in, often just a few million kilometers from the star. Planets in these zones orbit quickly, completing their years in days or weeks. Many are likely tidally locked, meaning one side always faces the star, while the other side is in eternal darkness. This creates extreme temperature differences, with the day side baked by constant starlight and the night side frozen. But if the planet has a thick enough atmosphere, winds could redistribute heat, making the planet more temperate overall. Some studies suggest that tidally locked planets could still be habitable, with a band of moderate temperatures around the terminator, the boundary between day and night. These worlds would be strange, but not necessarily lifeless. Planetary systems also contain more than just planets. Asteroids, comets, moons, and rings are all part of the cosmic architecture. In our solar system, the asteroid belt between Mars and Jupiter contains millions of rocky fragments, the leftover building blocks of planets that never quite finished forming. The Kuiper belt, beyond Neptune, is a region of icy bodies, including Pluto and countless comets. These small bodies are not just debris. They carry clues about the early solar system, preserving material that has barely changed in billions of years. Comets, when they plunge toward the sun and their ices vaporize, release dust and gas that can be analyzed, revealing the composition of the primordial disk. Asteroids, when studied or even visited by spacecraft, tell stories of heating, melting, and differentiation, processes that also shaped the planets. Moons, too, are part of the story. In our solar system, many moons are geologically active, or were in the recent past. Jupiter's moon Io is the most volcanically active body in the solar system, its interior heated by tidal forces from Jupiter's immense gravity. Saturn's moon Enceladus shoots geysers of water ice into space from a subsurface ocean, possibly heated by tidal friction. Europa, another moon of Jupiter, is thought to have a global ocean beneath its icy crust, kept liquid by tidal heating. These moons are potential habitats for life, places where liquid water exists not because of a nearby star's warmth, but because of gravitational interactions. Exomoons, moons orbiting planets in other solar systems, are much harder to detect than exoplanets, but they likely exist in great numbers. Some could be large, Earth-sized or even bigger, orbiting gas giants in the habitable zone. If such moons exist, they could be worlds with oceans, atmospheres, and perhaps life. Rings are another common feature. Saturn's rings are the most famous, a broad, flat disk of ice and rock particles extending tens of thousands of kilometers from the planet. But other planets have rings too. Jupiter, Uranus, and Neptune all have ring systems, though much fainter and less spectacular than Saturn's. Some exoplanets may also have rings, possibly even more impressive than Saturn's. When a planet transits in front of its star, blocking a tiny fraction of the starlight, the shape and timing of that transit can reveal features like rings. A few exoplanets show transit patterns that hint at massive ring systems, extending far beyond the planet itself, though confirming these interpretations is difficult. If rings exist around exoplanets, they could form from the breakup of moons, from captured comets, or from leftover material that never coalesced into a moon. They are transient features, slowly spreading and dissipating over millions of years, but while they last, they add beauty and complexity to the systems they adorn. Some solar systems are tightly packed, with multiple planets orbiting close to their star, all within the orbit of Mercury. These compact systems challenge ideas about orbital stability. In our solar system, planets are relatively well spaced, each in its own lane. But in compact systems, planets orbit shoulder to shoulder, with their gravitational interactions finely balanced. Some of these systems show orbital resonance, where the planet's orbital periods are related by simple ratios. For example, if one planet completes exactly 2 orbits for every 3 orbits of another, they are in a 2 to 3 resonance. These resonances help stabilize the system, preventing close encounters that would lead to collisions or ejections. Compact systems also reveal that planets can form efficiently in the inner regions of protoplanetary disks, building multiple worlds from relatively little material. The TRAPPIST-1 system is a remarkable example of a compact system. This red dwarf star, located 40 light-years from Earth, hosts 7 Earth-sized planets, all orbiting within a distance closer than Mercury is to the Sun. Several of these planets orbit in the habitable zone, where temperatures could allow liquid water. The planets are likely rocky and may have atmospheres, though whether those atmospheres are thick or thin, wet or dry, remains to be determined. The system's compactness and the presence of multiple, potentially habitable worlds make it one of the most intriguing targets for future study. If life exists on any of these planets, it could exist on several, separated by distances that, in cosmic terms, are tiny. A civilization arising on one planet might easily detect or even reach its neighbors, making the TRAPPIST-1 system a natural laboratory for thinking about life in the universe. Solar systems do not last forever. Over billions of years, stars evolve, and as they do, they alter the environments of their planets. When a star like the Sun exhausts the hydrogen in its core, it begins to burn hydrogen in a shell around the core, causing it to expand into a red giant. The outer layers swell outward, engulfing the innermost planets. Mercury and Venus will almost certainly be consumed when the Sun becomes a red giant in about 5 billion years. Earth's fate is less certain. It may be engulfed, or it may survive on a wider orbit, its surface seared to a barren cinder by the intense heat. After the red giant phase, the Sun will shed its outer layers, creating a glowing shell of gas called a planetary nebula. The core will shrink into a white dwarf, a dense, hot ember that will slowly cool over trillions of years. Any surviving planets will orbit this white dwarf, frozen and dark, the remnants of a once vibrant solar system. For more massive stars, the end is far more violent. When a massive star exhausts its nuclear fuel, it collapses and then explodes in a supernova, one of the most energetic events in the universe. The explosion can vaporize any nearby planets, scattering their atoms into space. Even planets at greater distances may be sterilized by the intense radiation. Yet, strangely, some planets do survive supernovae. Astronomers have found planets orbiting pulsars, the rapidly spinning neutron stars left behind by supernova explosions. These pulsar planets likely formed from the debris of the explosion, material that settled into a disk and coalesced into new worlds. They are second-generation planets, born from the ashes of the star's death, orbiting in a harsh environment of intense radiation and magnetic fields. Their existence shows that even destruction can lead to creation, that the cycle of stellar life and death is intimately connected to the formation of planetary systems. Throughout the galaxy, solar systems are forming, evolving, and dying in an endless cycle. Molecular clouds collapse, stars ignite, planets grow from dust. Those planets migrate, collide, and sometimes are ejected into the dark. Systems are disrupted by passing stars, reshaped by the gravitational pull of giant planets, and eventually destroyed when their stars age and die. But from that destruction, new material is scattered into space, enriched with heavy elements forged in the hearts of stars. This material joins new molecular clouds, which collapse to form new stars and new planets, continuing the cycle. The study of solar systems has exploded in the past few decades, driven by the discovery of thousands of exoplanets. Each new discovery refines our understanding, adding to the picture of how planets form, where they can exist, and what they might be like. Missions like Kepler, TESS, and soon the James Webb Space Telescope are revealing not just the presence of planets, but their atmospheres, their weather, their compositions. We are beginning to see exoplanets not as distant points of data, but as real worlds, each with its own story. Some are hellish, with molten surfaces or crushing atmospheres. Others are frozen, their skies dark, their landscapes silent. A few might be temperate, with liquid water, stable climates, and perhaps even life. As we drift through this knowledge, it is humbling to realize how small our solar system is in the grand scheme. The Sun is one star among hundreds of billions in the Milky Way. Our planets are a handful among countless worlds orbiting those stars. Yet our solar system is also unique, at least in the details. Its particular arrangement of planets, the presence of a large moon stabilizing Earth's climate, the migration of Jupiter that may have protected the inner planets, all these factors contributed to making Earth a world where life could flourish. Whether similar arrangements exist elsewhere, we do not yet know. But the sheer number of solar systems, the endless variety of their configurations, suggests that somewhere, perhaps many somewheres, other worlds with similar stories are waiting to be found. Solar systems are not just collections of planets, they are ecosystems, interconnected webs of gravitational interactions, chemical exchanges, and physical processes. In our solar system, Jupiter acts as a shepherd, its powerful gravity influencing the orbits of asteroids and comets, sometimes flinging them into the inner system, sometimes protecting the inner planets by capturing or deflecting incoming threats. Saturn plays a similar role. The asteroid belt is not just a random collection of rocks, but a region shaped by Jupiter's gravity, with gaps carved out by resonances. The Kuiper belt marks the outer boundary of the Sun's significant gravitational influence. Each component affects the others, creating a system that is stable yet dynamic, ordered yet constantly evolving. In other solar systems, these roles are played by different actors. A hot Jupiter, orbiting close to its star, would dominate the inner system, its gravity preventing other large planets from forming or surviving nearby. A system with two or more giant planets in resonance would have a different dynamic, with their combined influence shaping the distribution of smaller bodies. A system around a binary star would have zones where orbits are stable and zones where they are chaotic, with planets confined to the safe regions. Each system's architecture is a product of its unique history, the particular conditions of its formation, and the random events, close encounters, migration, collisions that shaped it over time. The beauty of solar systems lies in this diversity. No two are exactly alike. Each is a unique configuration of matter and motion, a stable pattern carved out of chaos by the universal laws of gravity and physics. And yet, despite their differences, all solar systems share a common origin. They all began as clouds of gas and dust, gathered by gravity, heated by collapse, and transformed through accretion and collision into the systems we observe. This common thread connects our solar system to every other system in the galaxy, a reminder that we are part of a larger cosmic story, one that spans the entire universe and reaches back to the very beginning of time. As you let these thoughts drift through your mind, imagine the countless solar systems scattered through the galaxy. Some are young, still forming, their planets growing from the dust of their protoplanetary disks. Others are mature, their planets long settled into stable orbits, perhaps hosting life that has evolved for billions of years. Still others are ancient, their stars dying, their planets facing the end of their worlds. Each system is a chapter in the grand narrative of the cosmos, and each holds the potential for discoveries that will deepen our understanding of the universe and our place within. The journey through solar systems is a journey through time and space, through creation and destruction, through order and chaos. It is a reminder that the universe is vast, far larger than we can fully grasp, yet it operates by rules we can understand. Gravity, motion, chemistry, light. These are the tools with which the universe builds its wonders. And among those wonders, solar systems stand out as places where matter organizes itself into structures of breathtaking complexity and beauty. Planets orbit stars, moons orbit planets, and all are bound together in a cosmic dance that has been unfolding for billions of years and will continue for billions more. In this endless variety, in this vast arena of worlds, solar systems offer a glimpse into the processes that shape the universe. They teach us about formation and evolution, about stability and change, about the delicate balance between forces that build and forces that destroy. They show us that planets are not rare, that solar systems are common, and that the ingredients for life may be scattered widely through the cosmos. And as we learn more, as our telescopes peer deeper and our instruments grow more sensitive, we move closer to answering one of humanity's oldest questions. Are we alone? The answer, whatever it may be, lies written in the stars, in the silent orbits of distant worlds, in the countless solar systems that fill the galaxy. Let your mind rest on these thoughts. Let the immensity of it all wash over you gently. There is no need to hold on to every detail, no need to remember every fact. Just let the wonder seep in, the quiet realization that the universe is filled with worlds, each one a story, each one a mystery. And somewhere, far out in the darkness, under alien skies lit by one sun, or two, or none at all, planets turn in their orbits, continuing the ancient dance that began with the first stars, and will end only when the universe itself grows cold and still. For now, though, the dance goes on, and we are here to witness it, to marvel at it, and to slowly, patiently learn its secrets. Solar systems form in many places, not just the calm outskirts of galaxies. Some are born in the crowded hearts of star clusters, where thousands of stars are packed into a small region of space. In these clusters, stellar nurseries produce stars in great numbers, and many of those stars have protoplanetary disks. The environment is harsh, with intense ultraviolet radiation from massive nearby stars that can strip material from disks, potentially stunting planet formation. Yet planets do form in these places, somehow managing to grow even amid the chaos. When they are found, these cluster planets offer clues about how planet formation proceeds under extreme conditions, where the disk is both fed by the surrounding gas cloud and eroded by the radiation of neighboring stars. Some stars form in isolation, far from clusters, in small, cold, molecular clouds. These stars may take longer to form, and their disks may be quieter, with less turbulence and fewer external influences. Planets forming around such stars might grow more slowly, but in more stable conditions, potentially leading to different outcomes. The variety of star-forming environments ensures that planetary systems form under a wide range of initial conditions, contributing to the diversity we observe. Planetary systems can also be influenced by their galactic environment. A solar system near the center of the galaxy experiences a higher density of stars, more frequent close encounters, and stronger tidal forces from the galaxy itself. These factors can perturb orbits, eject planets, or even disrupt entire systems. Systems in the galactic halo, the sparse region above and below the galactic disk, are more isolated, less likely to be disturbed by neighbors. Our own solar system orbits in a relatively quiet part of the galaxy, far from the center but not too far out, in a region where the density of stars is moderate and the environment is stable. This may be part of the reason Earth has remained habitable for billions of years, a stroke of cosmic luck that placed us in a safe neighborhood. Migration and dynamical evolution are not the only forces shaping solar systems. Collisions play a crucial role, especially in the early stages. The Moon, Earth's largest natural satellite, is thought to have formed from a giant impact between the young Earth and a Mars-sized body called Theia. The collision vaporized parts of both planets, ejecting material into orbit around Earth. This material coalesced into the Moon, which has since stabilized Earth's axial tilt, helping to moderate our climate. Without the Moon, Earth's axis would wobble chaotically over time, leading to extreme climate swings that might have made the development of complex life more difficult. Giant impacts are common in the early days of planetary systems, and they can have profound effects, creating moons, altering orbits, stripping away atmospheres, or even destroying planets. In some systems, planets may collide and merge. When two planets of similar size meet, the result can be a larger planet with a complex internal structure, perhaps with two cores that eventually merge, or layers of different compositions that take billions of years to fully mix. These merged planets might have unusual properties, higher densities than expected, or strange magnetic fields. Detecting such features in exoplanets is challenging, but as our instruments improve, we may find evidence of ancient collisions in the masses, densities, and compositions of distant worlds. Atmospheres, too, tell stories of a planet's history. Some planets have thick atmospheres, tens or hundreds of kilometers deep, composed of hydrogen, helium, or carbon dioxide. Others have thin atmospheres, barely clinging to the surface, or no atmosphere at all, stripped away by stellar winds or impacts. The composition of an atmosphere depends on many factors. The planet's mass, which determines whether it can hold onto light gases like hydrogen. Its distance from the star, which affects temperature and atmospheric chemistry. And its history of impacts, volcanism, and interaction with the solar wind. By studying exoplanet atmospheres, using techniques like transit spectroscopy, astronomers can detect molecules like water vapor, methane, carbon dioxide, and even oxygen, building up a picture of what these distant worlds are like. Some planets have atmospheres so thick and opaque that their surfaces are hidden from view. Venus is an example in our own solar system, shrouded in clouds of sulfuric acid, with a surface pressure 90 times that of Earth. Exoplanets around other stars may have even more extreme atmospheres, clouds made of vaporized rock or metal, winds howling at thousands of kilometers per hour, layers of haze that trap heat and create runaway greenhouse effects. Others have clear skies, where starlight reaches the surface unimpeded, creating conditions vastly different from cloud-covered worlds. The diversity of planetary atmospheres reflects the diversity of planetary conditions. Temperature, pressure, composition, and history all leave their marks. On Earth, life has profoundly altered the atmosphere, producing oxygen through photosynthesis. Detecting oxygen or other biosignature gases in an exoplanet's atmosphere would be a strong hint, though not definitive proof, of life. It is one of the primary goals of future missions, to find a world with an atmosphere that suggests biological processes, a world where life might have taken hold and transformed its environment, just as life transformed Earth. As we explore these ideas, drifting from one concept to the next, let your breathing slow and deepen. There is no rush, no urgency. The universe has been unfolding for nearly 14 billion years, and solar systems have been forming, evolving, and changing for most of that time. Our understanding grows slowly, built up piece by piece through observation, theory, and careful analysis. Each new discovery adds to the picture, refining our models and deepening our appreciation for the complexity and beauty of planetary systems. Planetary systems, in all their variety, are natural experiments in physics and chemistry, laboratories where the laws of nature play out over immense spans of time. By studying them, we learn not just about planets, but about the fundamental processes that govern the universe. Gravity, thermodynamics, orbital mechanics, chemical reactions, and the interactions between matter and energy. These processes are universal, operating the same way everywhere, from the smallest scales to the largest. And because they are universal, we can understand them, predict them, and use that understanding to explore the cosmos. The search for solar systems, and especially for habitable worlds, is driven by curiosity, by the desire to know whether we are alone in the universe. It is one of the most profound questions we can ask, and the answer, whatever it turns out to be, will have profound implications. If we find life elsewhere, it will tell us that life is common, that the universe is filled with it, and that the processes that led to life on Earth are not unique. If we do not find life, or find that it is exceedingly rare, it will tell us that Earth is special, that the conditions here are rare, or that the emergence of life requires circumstances that almost never align. Telescopes continue to scan the skies, detecting the faint dimming of starlight as planets transit, or the subtle wobble of stars tugged by orbiting worlds. Radio antennas listen for signals that might indicate technological civilizations. Robotic probes explore the moons of Jupiter and Saturn, searching for signs of life in subsurface oceans. And all the while, new solar systems are discovered, each one adding to our understanding, each one expanding the boundaries of what we thought possible. Solar systems with planets orbiting pulsars remind us that worlds can exist in the most unlikely places. Pulsars are neutron stars, the collapsed cores of massive stars that exploded in supernovae. They spin rapidly, sometimes hundreds of times per second, emitting beams of radiation that sweep across space like lighthouse beams. When planets orbit pulsars, they are bathed in intense radiation and magnetic fields, conditions that would seem utterly hostile to any form of matter, let alone life. Yet several pulsar planets have been discovered, detected through tiny variations in the timing of the pulsar's radio pulses caused by the gravitational tug of the orbiting planets. The first pulsar planets were discovered in 1992, orbiting the pulsar PSR 1913+16. These planets are thought to have formed from the debris disk that surrounded the pulsar after the supernova, material rich in heavy elements forged in the explosion. They are second-generation worlds, born from destruction, orbiting in an environment vastly different from anything in our solar system. The radiation from the pulsar is intense, sterilizing the surfaces. But the fact that planets can exist there at all expands our understanding of where planetary systems can form. Even the death of a star can give rise to new worlds. Some planets are almost entirely made of water. These water worlds are unlike anything in our solar system, where even Earth, with its vast oceans covering 70% of its surface, contains water that makes up less than 0.1% of its total mass. But astronomers have discovered exoplanets where water may comprise 25%, 30%, or even 50% of the planet's mass. These are true ocean worlds, potentially covered by seas hundreds or even thousands of kilometers deep. The closest comparison would be some of the icy moons in our outer solar system, like Europa, Enceladus, or Titan, have subsurface oceans beneath shells of ice. But water-world exoplanets are much larger, with their oceans potentially exposed at the surface or hidden beneath thick atmospheres of water vapor. The first confirmed water worlds were discovered in the Kepler-138 system, located 218 light-years from Earth. Two planets in this system, Kepler-138c and Kepler-138d, have densities much lower than rocky planets like Earth, yet higher than gas giants. Their masses and sizes suggest they must be composed largely of water. Imagine a planet with oceans over 1,500 kilometers deep, more than 500 times deeper than Earth's deepest ocean trench. The pressure at such depths would be immense, millions of times the pressure at Earth's surface. Under such conditions, water behaves strangely. It can form exotic types of ice that exist only at extreme pressures and temperatures, phases like Ice 7 or Ice 10, where water molecules are locked into crystalline structures despite temperatures that would normally keep water liquid. Above these deep oceans, the planets might have thick atmospheres of water vapor, clouds of steam extending thousands of kilometers into space. Beneath the atmosphere, the ocean could be liquid near the surface, transitioning to supercritical water deeper down. Supercritical water is a strange state of matter, not quite liquid and not quite gas, with properties of both. It flows like a gas, but has the density of a liquid. In this state, water can dissolve minerals and transport heat in ways that don't occur in ordinary liquid water. The chemistry of such oceans would be completely alien, potentially hosting forms of life adapted to high pressure and strange solvents. Water worlds likely form in the outer regions of planetary systems, beyond the frost line where ice can condense. But many migrate inward, drawn toward their stars by interactions with the protoplanetary disk or other planets. As they move closer to the star, the outer layers of ice melt, creating deep global oceans. If they migrate too close, the water evaporates entirely, leaving behind a rocky or metallic core. But at the right distance, they remain ocean worlds, potentially habitable if conditions are right. Some water worlds orbit in the habitable zones of their stars, where temperatures are moderate enough for liquid water to exist at the surface. These are prime targets in the search for life beyond Earth. Discovering water worlds has changed how astronomers think about habitability. For decades, the assumption was that a planet needs plate tectonics, volcanism, and a carbon cycle to regulate its climate over billions of years. Earth's long-term stability comes from the cycling of carbon dioxide between the atmosphere, oceans, and rocks, driven by volcanism and the weathering of continental rocks. But on a water world with no continents, no exposed rock, this cycle cannot operate. Yet, simulations suggest that water worlds can remain habitable for over 1 billion years, even without these processes, if they start with the right amount of carbon dioxide in their atmospheres. The water acts as a buffer, absorbing heat and moderating temperature swings, while the sheer volume of the ocean provides a stable environment where life could evolve. Not all planets have such abundant water. Some are dry, with little or no water at all. These desert worlds might be rocky, with surfaces baked by their stars, atmospheres thin or absent, and no oceans to moderate their climates. They form in the inner regions of planetary systems, where temperatures are too high for ice to condense, or they lose their water over time through impacts, atmospheric escape, or incorporation into the planet's interior. Venus is an example from our own solar system, a world that may once have had oceans, but lost them as a runaway greenhouse effect evaporated the water into the atmosphere, where ultraviolet light from the sun broke it apart. The hydrogen escaped into space, and the planet became the scorching, dry world it is today. Other planets may have water, but locked away beneath their surfaces. These worlds, with subsurface oceans hidden under ice or rock, are common in our own solar system. Europa, a moon of Jupiter, has a global ocean beneath an icy crust, perhaps 10 to 15 kilometers thick. Tidal heating from Jupiter's gravity keeps the ocean liquid despite Europa's distance from the Sun. Enceladus, a small moon of Saturn, also has a subsurface ocean, evidenced by plumes of water vapor and ice erupting from cracks near its south pole. These plumes contain organic molecules and salts, suggesting that the ocean is in contact with a rocky seafloor, where hydrothermal vents might exist, providing energy for life. In exoplanet systems, similar moons might orbit gas giants in the habitable zone, their subsurface oceans warmed by tidal forces, creating hidden refuges for life. Atmospheres on exoplanets come in endless variety. Some are thick and opaque, shrouding the planet in perpetual clouds. Others are thin and transparent, allowing starlight to reach the surface unimpeded. The composition depends on the planet's mass, temperature, and distance from the star. Close to the star, atmospheres can be stripped away by stellar winds and intense radiation. Farther out, gases condense and fall as rain or snow, altering the atmosphere's composition over time. On some hot planets, the atmosphere itself can contain exotic molecules and compounds. Vaporized metals like sodium, potassium, and iron have been detected in the atmospheres of hot Jupiters, glowing in the intense heat. One of the strangest classes of exoplanets is the lava world. These planets orbit so close to their stars that their surfaces are molten. Oceans of liquid rock covering continents of barely solidified crust. The temperature can reach thousands of degrees, hot enough to vaporize rock and create an atmosphere of silicates and metals. On the day side, the surface might be a glowing sea of magma, while the night side cools enough for rock to solidify, creating a bizarre cycle of melting and freezing. Winds howl at supersonic speeds, carrying vaporized minerals from the day side to the night side, where they condense into clouds and rain back down as droplets of molten rock or even pebbles of solidified lava. These worlds are hellish, utterly inhospitable to any form of life we can imagine, but they reveal the extremes of planetary conditions. Another exotic type is the superpuff, sometimes called a cotton candy planet. These are gas giants with incredibly low densities, less than that of styrofoam. They have masses comparable to Earth, but radii larger than Neptune, giving them densities so low they would float in water if such a thing were possible. Their atmospheres are extended and tenuous, puffed up by heat from their star or from internal processes. How they form is still a mystery. It may be that they formed quickly in the early stages of the protoplanetary disk, capturing huge amounts of gas before the disk dissipated. Or they might be planets that lost their heavier elements, leaving behind only a bloated envelope of hydrogen and helium. Superpuffs are fragile, their atmospheres slowly eroded by stellar winds, and they may eventually shrink into more typical gas giants, or even lose their atmospheres entirely, becoming rocky cores. Planetary atmospheres can also reveal the presence of life. On Earth, oxygen makes up 21% of the atmosphere, almost all of it produced by photosynthetic organisms over billions of years. Before life, Earth's atmosphere had almost no oxygen. If astronomers detect oxygen, along with methane or other gases that react with oxygen and must be continually replenished, it could be a sign of biological activity. Future telescopes, like the James Webb Space Telescope, are capable of analyzing the atmospheres of some exoplanets, looking for these biosignatures. The detection of oxygen or methane alone is not definitive proof of life, as these gases can also be produced by non-biological processes. But finding them together, in the right proportions, would be a strong hint that something living is modifying the planet's atmosphere. Some planets have skies filled with clouds of unusual materials. On Earth, clouds are made of water droplets or ice crystals. But on exoplanets, clouds can be made of silicates, forming particles that shimmer like tiny glass beads. On some hot Jupiters, clouds of corundum, the mineral that makes up sapphires and rubies, have been detected. These worlds might experience rain made of molten gemstones, with winds carrying droplets of liquid minerals across the sky. On colder planets, clouds could be made of ammonia, methane, or even sulfur compounds, creating hazes of different colors: yellow, orange, brown, or deep red. The diversity of clouds reflects the diversity of planetary conditions, each world with its own unique weather. The study of exoplanet weather is a growing field. By observing how the brightness of a planet changes over time, astronomers can detect weather patterns, storms, and cloud movements. Some hot Jupiters show strong temperature differences between their day and night sides, with heat transported by powerful jet streams. Others have more uniform temperatures, suggesting that their atmospheres are efficient at redistributing heat. On some planets, storms as large as Jupiter's Great Red Spot, a hurricane that has raged for centuries, might exist, visible as dark or bright spots in telescope observations. Understanding exoplanet weather helps astronomers predict what these worlds are like and whether they might be habitable. Tidal locking is common among planets that orbit close to their stars. A tidally locked planet always shows the same face to its star, just as the Moon always shows the same face to Earth. This happens because the star's gravity creates tidal bulges on the planet, and over time, friction from these bulges slows the planet's rotation until it matches its orbital period. The result is a world with perpetual day on one side and perpetual night on the other. The day side can be scorching hot, while the night side freezes. But the boundary between the two, the terminator, might have moderate temperatures, creating a band where conditions are more temperate. For a long time, astronomers thought tidally locked planets would be uninhabitable. The extreme temperature differences would create fierce winds, and any atmosphere might freeze out on the night side, leaving the day side airless. But recent climate models suggest that if the planet has a thick enough atmosphere, winds can redistribute heat, making the entire planet more habitable. The atmosphere acts as a blanket, transporting warmth from the day side to the night side and preventing the complete freeze-out of gases. Some tidally locked planets might even have stable climates, with clouds forming over the subsolar point, the spot directly facing the star, reflecting some of the starlight and cooling the day side. These planets could have permanent storm systems, cyclones trapped over the hottest regions, their structure maintained by the constant influx of energy from the star. Red dwarf stars, the most common type of star in the galaxy, have habitable zones very close to the star. Planets in these zones orbit in days or weeks and are almost certainly tidally locked. This means that a large fraction of potentially habitable planets in the galaxy might be tidally locked. If life can thrive on such worlds, it would vastly increase the number of habitable planets in the universe. But red dwarfs are also active, emitting powerful flares that can bathe their planets in intense radiation. Whether life can survive such conditions is an open question. But some studies suggest that a thick atmosphere or a strong magnetic field could protect the planet's surface, creating niches where life might take hold. Magnetic fields play a crucial role in a planet's habitability. Earth's magnetic field, generated by the motion of molten iron in its core, acts as a shield, deflecting charged particles from the solar wind and preventing the atmosphere from being stripped away. Mars once had a magnetic field, but it shut down billions of years ago, and without its protection, the solar wind gradually eroded Mars's atmosphere, turning it from a potentially habitable world into the cold, dry planet we see today. Exoplanets with strong magnetic fields are more likely to retain their atmospheres over billions of years, making them better candidates for habitability. Detecting magnetic fields on exoplanets is challenging, but astronomers are developing techniques to look for the radio emissions produced when stellar winds interact with a planet's magnetosphere. Some planets are so massive, they approach the boundary between planet and star. These are super-Jupiters, gas giants with masses 10, 15, or even 20 times that of Jupiter. They are so massive that they generate significant heat from their own gravitational contraction, glowing faintly in infrared light. At around 13 Jupiter masses, the core becomes hot and dense enough for deuterium fusion to occur, a process that marks the transition from planet to brown dwarf. Brown dwarfs are sometimes called failed stars because they are not massive enough to sustain hydrogen fusion, the process that powers true stars. The boundary between the most massive planets and the least massive brown dwarfs is blurry, and astronomers debate whether the distinction should be based on mass, formation process, or something else. Planetary systems can also contain objects that don't fit neatly into categories. Dwarf planets, like Pluto in our solar system, are large enough to be rounded by their own gravity, but have not cleared their orbits of other debris. They exist in regions crowded with smaller bodies, part of a population rather than a solitary planet. In exoplanet systems, similar objects likely exist. Small worlds orbiting in belts or clusters, too numerous to be called planets, but too large to be mere asteroids. These objects might be pristine remnants from the early days of the system, preserving material that never got incorporated into larger planets, offering clues about the composition of the original protoplanetary disk. The architecture of a planetary system, the arrangement of planets, their sizes, masses, and orbits, tells the story of how the system formed and evolved. Some systems are tightly packed, with multiple planets orbiting closer to their star than Mercury is to the Sun. Others are spread out, with planets at great distances, cold and dark. Some have planets in resonance, their orbital periods locked into simple ratios, a sign that they migrated together or captured each other into stable configurations. Others have planets on tilted or eccentric orbits, evidence of past gravitational encounters or the influence of distant companion stars. Astronomers are learning to read these stories. By measuring the masses, sizes, and orbits of exoplanets, and by studying the composition of their atmospheres, they can reconstruct the history of the system. Did the planets form where they are now, or did they migrate? Were there collisions that reshaped the system? Is there evidence of other planets, unseen but betrayed by their gravitational influence? Each planetary system is a puzzle, and the clues are scattered across the data, waiting to be pieced together. The James Webb Space Telescope launched in 2021, is revolutionizing the study of exoplanets. Its powerful infrared vision can peer through the dusty clouds of star-forming regions, observing planets as they grow in their protoplanetary disks. It can analyze the atmospheres of exoplanets with unprecedented precision, detecting molecules like water, carbon dioxide, methane, and even potential biosignatures. Its observations of distant worlds are revealing atmospheres of astonishing complexity, weather patterns, and chemical processes that were only theoretical before. With each new observation, our picture of exoplanets becomes richer and more detailed. Future missions will go even further. Telescopes designed specifically to image exoplanets directly, rather than relying on transits or radial velocity measurements, will be able to study planets around nearby stars in exquisite detail. They will map the surfaces of these worlds, looking for continents, oceans, clouds, and seasonal changes. They will search for technosignatures, signs of advanced civilizations, artificial lights on the night side of planets, or industrial pollutants in their atmospheres. The search for life beyond Earth is entering a new era, one where we may finally answer the question, are we alone? As we drift deeper into these thoughts, the sheer scale of it all becomes almost overwhelming, yet also strangely comforting. The universe is vast, filled with an uncountable number of worlds, each one a unique expression of the laws of nature. Some are like Earth, rocky and temperate, with oceans and atmospheres. Others are wildly different, with lava seas, diamond mantles, or skies of vaporized metal. And among all these worlds, somewhere, perhaps on many somewheres, life may have emerged, adapting to conditions we can barely imagine, thriving in environments that would be deadly to us, but are perfectly suited to them. The diversity of solar systems also teaches us about our own place in the cosmos. For a long time, we thought our solar system was typical, a template for understanding all planetary systems. But the discovery of exoplanets has shown that we are, in many ways, unusual. We don't have a hot Jupiter or a super Earth. Our giant planets are far from the Sun, not close in. Our terrestrial planets are relatively small, and our asteroid belt is thin compared to some systems. Whether this makes us rare or just one variant among many is still unclear. But it does suggest that the specific arrangement of our solar system, the one that gave rise to life on Earth, may not be the most common configuration. It may be a lucky accident, a particular roll of the dice in the great game of planet formation. And yet, the fact that planets are so common and that many orbit in habitable zones gives hope. Even if Earth-like planets are rare, there are so many stars, so many planets, that the sheer number of opportunities for life to arise is staggering. The Milky Way alone contains hundreds of billions of stars, and most of them have planets. If even a tiny fraction of those planets are habitable, and if even a tiny fraction of habitable planets develop life, the galaxy could be teeming with living worlds. And beyond the Milky Way, there are billions of other galaxies, each with its own countless stars and planets. The universe may be far more alive than we ever imagined. The search for life is not just about finding microbes or plants. It's also about the possibility of finding intelligent life. Civilizations that have developed technology, built cities, and perhaps even ventured into space. The question of whether we are alone in the universe is one of the most profound we can ask. If we find that life is common, it will tell us that the processes that led to life on Earth are universal, that the universe is fertile ground for biology. If we find that life is rare, it will tell us that Earth is precious, a rare jewel in a vast and mostly barren cosmos? Either answer will change us. For now, the search continues. Telescopes scan the skies, listening for radio signals, watching for the faint glints of reflected starlight from distant worlds. Spacecraft explore our own solar system, drilling into ice, analyzing rocks, searching for signs of past or present life on Mars, Europa, Enceladus, or Titan. And with each passing year, our technology improves, our understanding deepens, and the possibility of discovery grows. We are living in an extraordinary time, a moment in history when humanity is beginning to answer questions that have been asked for millennia. The planets of our solar system have been companions to humanity for as long as we have looked up at the sky. Mercury, Venus, Mars, Jupiter, and Saturn were known to ancient astronomers, who tracked their movements and wove them into myths and stories. They were the wanderers, objects that moved against the fixed stars, mysterious and powerful. Even before we understood what they were, they captured our imagination. And now, thousands of years later, we have sent spacecraft to visit them, landed robots on their surfaces, and learned their secrets. We know them as worlds, each with its own character, its own story. And beyond our solar system, thousands of other planets are joining the list of known worlds. Each discovery is a reminder that the universe is richer, stranger, and more beautiful than we ever thought. The hot Jupiters, the super-Earths, the water worlds, the lava planets, all of them expand our understanding of what a planet can be. They challenge our theories, push the boundaries of our knowledge, and inspire us to keep searching, keep exploring, keep asking questions. Solar systems are not just collections of planets and moons. They are ecosystems, dynamic systems where everything is connected. The star provides energy, warming the planets and driving weather. The planets interact gravitationally, shaping each other's orbits, sometimes stabilizing, sometimes destabilizing. Moons orbit planets, some geologically active, others dead and cratered. Asteroids and comets are leftovers from formation, reservoirs of pristine material, and occasional threats when they collide with planets. Everything is in motion, everything is changing, slowly, patiently, over timescales that dwarf human history. In our solar system, the planets have been slowly drifting, their orbits changing in subtle ways over billions of years. Jupiter and Saturn, through their gravitational interactions, have nudged each other, and their influence has shaped the asteroid belt and the Kuiper belt. The Moon is slowly moving away from Earth, its orbit expanding by about 4 centimeters per year, as tidal forces transfer angular momentum. Mars is gradually having its thin atmosphere stripped away by the solar wind. These changes are slow, but they are real, and over billions of years they add up. Our solar system is not static. It is evolving, and it will continue to evolve long after humanity is gone. Other solar systems are evolving too. Planets migrate, collide, or are ejected. Stars age, growing brighter or cooler over billions of years, shifting the location of the habitable zone. Some systems will remain stable for the entire lifetime of their star. Others will experience catastrophic events, collisions that shatter planets, close encounters with other stars that disrupt orbits, or the death of the star itself in a supernova or planetary nebula. The galaxy is filled with solar systems at every stage of evolution, from young systems still forming to ancient systems billions of years older than our own, their planets long since frozen or vaporized. The future of our own solar system is written in the physics of stellar evolution. In about 5 billion years, the Sun will exhaust the hydrogen in its core, and begin to expand into a red giant. Its outer layers will swell, engulfing Mercury and Venus, and possibly Earth. Even if Earth escapes being swallowed, it will be seared by the intense heat, its oceans boiled away, its atmosphere stripped, leaving behind a lifeless, molten rock. The outer planets will warm, their icy moons perhaps briefly becoming habitable as the sun's expanded envelope bathes them in heat. But this warmth will be short-lived. The sun will shed its outer layers, creating a glowing shell of gas, a planetary nebula, and the core will collapse into a white dwarf, a dense, slowly cooling ember. The surviving planets will orbit this white dwarf, frozen and dark for trillions of years as the white dwarf cools to invisibility. But before that end, life on Earth will have long since become impossible. As the sun ages, it grows slightly brighter, and in about 1 billion years, the increased heat will trigger a runaway greenhouse effect, evaporating the oceans and rendering Earth uninhabitable. If humanity or its descendants still exist, they will need to leave Earth, migrating to the outer solar system or to other stars. The story of life on Earth may be just one chapter in a much longer story, one that continues on other worlds, under other suns. These thoughts, grand and sweeping, are also deeply personal. We are made of stardust, quite literally. Every atom in your body, except for hydrogen, was forged in the heart of a star or in the explosion of a supernova. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created billions of years ago in stellar furnaces and scattered into space when those stars died. That material drifted through the galaxy, joined a cloud of gas and dust, and eventually became part of the solar nebula that formed the sun and planets. Some of it ended up on Earth, and some of it ended up in you. In a very real sense, we are the universe looking at itself, matter organized in such a way that it can think, wonder, and ask questions. We are part of the cosmos, not separate from it, and our drive to explore, to understand, to reach out and touch other worlds, is the universe's way of knowing itself. Every time you look up at the night sky, you are connecting with something vast and ancient, something that stretches across space and time, linking you to the stars, to distant galaxies, and to the possibility of other minds looking up at their own skies, asking the same questions. The study of solar systems, of exoplanets and planetary formation, is ultimately about understanding our origins. Where did we come from? How did the sun and planets form? What made Earth habitable? Are there other worlds like ours? And if so, do they harbor life? These questions drive us forward, inspiring missions, telescopes, and discoveries that push the boundaries of human knowledge. And as we find answers, new questions emerge, deeper and more intriguing, pulling us further into the mystery. There is a quiet beauty in this process, in the slow accumulation of knowledge, the careful observation, the thoughtful analysis. Science is not just about facts and figures. It is about wonder, about looking at the universe with open eyes and an open mind, willing to be surprised, willing to change our understanding when the evidence demands it. The story of solar systems is still being written. Every new discovery adds a sentence, a paragraph, a chapter. And we are all part of that story, not just as observers, but as participants, as conscious beings capable of marveling at the beauty and complexity of the cosmos. As the night deepens and your thoughts begin to drift, let these images settle in your mind. Planets orbiting twin suns, their skies painted with double shadows. Rogue worlds wandering through the dark, lit only by the faint glow of their own fading heat. Water worlds with oceans deeper than we can imagine, their surfaces hidden beneath miles of water and steam. Lava planets where the ground itself is molten, glowing red and orange under alien stars. And somewhere, perhaps, a world like Earth, with green forests and blue oceans, where life has taken hold and is flourishing, evolving, reaching toward its own sky, wondering if it is alone. All of this is real. All of this exists. Not in stories or dreams, but out there in the universe, scattered across the galaxy and beyond. The planets are turning, the stars are shining, and the great slow dance of gravity and motion continues, as it has for billions of years, as it will for billions more. And you, here in this moment, are part of it. You are connected to it all, a thread in the cosmic tapestry, a small but essential part of the vast and ancient story of the universe. Let your breathing slow. Let your body relax. The universe is vast, but it is also patient. It has been here for nearly 14 billion years, and it will be here long after you wake. There is no hurry, no urgency. The stars will wait. The planets will continue their orbits. The galaxies will turn. And you have done enough for today. You have journeyed through solar systems, through space and time, through wonder and mystery. You have touched the infinite and brought back a sense of awe. Now it is time to rest. Close your eyes and let the darkness embrace you, soft and warm. Let your thoughts drift like clouds, shapeless and free. Feel the weight of your body sinking into the bed, the gentle rise and fall of your breath, the quiet rhythm of your heartbeat. You are safe. You are home. And somewhere, out there in the endless night, countless worlds are spinning through the cosmos, each one a story, each one a mystery, each one a testament to the beauty and complexity of existence. Sleep now and dream of distant skies. Dream of planets you will never visit but can still imagine. Dream of oceans that stretch beyond the horizon, of mountains taller than Everest, of canyons deeper than any on Earth. Dream of twin suns setting together, casting long shadows across alien landscapes. Dream of starlight reflecting off icy moons, of auroras shimmering in magnetospheres, of comets tracing bright arcs through the dark. And when you wake, the universe will still be here, still turning, still full of wonders waiting to be discovered. But for now, rest. Let the cosmos carry you gently into sleep, cradled by the knowledge that you are part of something vast and beautiful, something that connects us all, from the smallest particle to the largest galaxy, from the first moment of the Big Bang to the present day, and into the far future. The universe is infinite in its variety and beauty. Solar systems are just one small part of that vastness, but they are our part, the worlds we can see and study and dream about. They remind us that we are not alone, that we are surrounded by countless other worlds, each with its own story. And as we drift off to sleep, we can take comfort in that. We are part of the cosmos, and the cosmos is vast, ancient, and endlessly fascinating. Good night, rest well, and may your dreams be filled with stars.